In this video, we have two more examples of some improper integrals. And I'm going to look at this first one and see that it is a fraction. And I guess, if I think about doing a little substitution, if I could make u the natural log of x, then du is 1 over x dx. And I'm going to be able to take out that x in the denominator. So my integral would become 1 over u squared du. Okay, now I should redo my bounds. Okay, so e, if I plug that in, the natural log of e is 1. Now the natural log of infinity is still infinity. So let me now do this with a limit statement. And again, I know a lot of people don't think about the limit statement. You just go. But remember, on the AP exam, if this were a free response, you're expected to know what the proper notation is. And the proper notation is to use the limit statement because we're not finding the area. We're finding what the area approaches. And this is one of those shortcuts that I know on multiple choice and on homework people sometimes skip. But to be correct, you really should do it with a limit statement. Okay, so let me raise the power and divide by the new power, evaluating at b and 1, doing the limit as b approaches infinity. Well, this is the same as negative 1 over u, evaluated at b and 1. At this point, if you had wanted to go back and write natural log, you certainly could have. You just go back to your original bounds. Remember, e and infinity are the bounds in terms of x. 1 and infinity are the bounds in terms of u. So if you stay in terms of u, you've got to use the u bounds, which I always think if you've gone to work to find them, you might as well use them. So I've got negative 1 over b minus negative 1 over 1, doing the limit as b approaches infinity. Well, as 1 over infinity we've dealt with before, this is going to get closer and closer to 0. So 0 minus negative 1 is 1. And that is what our area approaches. Okay, in this example, we still are doing an improper integral because we're going to infinity, but you'll see now we're dealing with some integration by parts because we have a product and substitution won't work with it. So let me start this way. Let me rewrite it right away with this limit statement. But let me kind of go off to the side here and let's think about how we could do this integral. Now this is one where we could use our shortcut, where we pick u to be x, derivative. We pick dv to be e to the negative x, antiderivative, and then we just connect them like that. Okay, so we end up with negative x e to the negative x minus e to the negative x, evaluated at b and 0. And we're doing the limit as b approaches infinity. Okay. Now, I might think about it this way. I might rewrite this with positive exponents. So let's say we had negative x over e to the x minus 1 over e to the x, evaluated at b and at 0. So if I plug in b, let me write my limit statement here, I get negative b over e to the b minus 1 over e to the b. If I plug in 0, I get 0 minus, well, e to the 0, remember, is 1, so 1 over 1 is 1. And I'm taking the limit as b approaches infinity. Well, let's deal with what's easy, maybe. This first statement, 1 over e to the infinity, this is obviously going towards 0. This one is a little bit harder, and I think a lot of people have a general feel that because the top is linear and the bottom is exponential, that it's probably approaching zero. But kind of out to the side here, let me talk about how we could do that with L'Hopital's rule. Because if I plug in infinity, I do get an infinity over infinity. That's one of those indeterminate forms that L'Hopital's rule works for. So I could take the derivative. The derivative of negative b is negative 1. The derivative of e to the b is e to the b. So now you plug in infinity and you see that, oh yeah, it definitely does approach 0 by L'Hopital's rule. So I have 0 minus negative 1 for an answer of 1. So a lot of pieces to this. First of all, we had to use integration by parts. I was able to do it with our kind of shortcut tic-tac-toe method. You wouldn't have had to. You certainly could have used the Magic 7, the UDV method. I rewrote it with positive exponents because I think a lot of times when you rewrite with positive exponents, the limits are easier. I plugged in b and I plugged in 0, and then I had to, this was an easy one. This one I kind of looked at L'Hopital's rule. I took the derivative of the top, derivative of the bottom, and I found out that in fact it did approach 0. And that's kind of what my intuition would have said, but at least I was able to verify it with L'Hopital.